Hello guys, this is Prime Concepts. You're welcome to my channel once again. Now in this video, we'll be analyzing the concepts. We'll be looking at the applications of Gauss Law. In our previous video, we studied Gauss Law. We understood what Gauss Law actually represents. So in this video, we want to look at the places we can apply Gauss Law so that we know why we actually study Gauss Law, right? Yes. Now we'll be looking at a few applications, about 3 applications of Gauss law to electric field. Now the first thing, let me quickly remind you, a quick reminder, that Gauss law simply says that the net flux through an enclosed surface is proportional to the charge enclosed, which means mathematically, Gauss law is given as flux, the net flux through an enclosed surface is Q, the charge enclosed, divided by permittivity of free space. So this is Gauss law mathematically. Now I want to look at how we can use Gauss law to determine electric field at certain points when you have a charge enclosed, right? That charge would radiate electric field. So we want to look at what will be the strength of the electric field at certain points from the charge that is enclosed. So the first application of Gauss law we would consider in this video is electric field. So let me call it one. Is electric field. Electric field due to a spherical charge. So we want to look at electric field due to a spherical charge. Now say we have a spherical charge like this. This is a spherical charge. We're going to consider the electric field at certain points from this spherical charge that has a radius. The radius of this spherical charge, I'm going to call it R. Of course, when you say this is a spherical charge, you should know that for a spherical charge or for any surface, the charge is usually at the surface of that system. So if this is a spherical charge, it means that the charges would lie at the edges of the sphere. So this is what we have for a spherical charge, right? Now we're going to consider 3 conditions for a spherical charge. The first condition we are going to look at is if what would be the electric field at a point outside the spherical charge. So I'm going to write it E field at a point outside the charge. So that is to say the distance we are considering is r, which is greater than the radius of the sphere. So this is the distance, the point, and then is greater than the radius of that sphere. Now, if we want to consider the electric field at a point outside the spherical charge, say we are choosing this point, say we are considering this point, right? According to Gauss law, we need to enclose this charge with a Gaussian surface. So we're going to enclose this charge with a spherical Gaussian surface, and then we can analyze the electric field at this point. So I'm going to do just that. I'm going to enclose this charge like this with a spherical surface, so that the radius of this spherical surface is the distance from the center to this, which is small r. So the electric field, if you recall, Gauss law says that phi is equal to EA, right? And then phi again, which is flux, is also equal to the charge enclosed divided by epsilon naught. Now, since this is a spherical, the surface we are using to enclose this charge is a spherical surface, and you know the area of a sphere. The area of a sphere is 4 pi r squared. So what it simply means is I would have E times 4 pi r squared, because the radius of this spherical surface is small r. So that's why I'm saying 4 pi small r squared equals what now? Charge enclosed divided by epsilon naught. So since I'm trying to find the electric field at this point, I would make E the subject. So if I find E, E becomes charge enclosed divided by what now? 4 pi. If I bring this down, I'm dividing by this, by 4 pi r squared. So 4 pi r squared epsilon naught. Or better still, the way we know, I'll put epsilon naught first. So I can simply write this as 4 pi epsilon naught r squared. So this electric field at a point outside a spherical charge. So it is given as E equals charge divided by this, which is what we have known from Gauss Law, right? Yes, so you see that the Gauss Law also verifies that this is actually true, right? So this is the first application under electric field due to a spherical charge. The next thing we want to consider the electric field at a point on the surface of that spherical charge, not outside now, at a point on the surface. What would the electric field be? So let me quickly rub this. Do well to always take note while you're copying this and stick to this video till the end. I'll be giving some powerful tips towards the end of this video you don't want to miss. Now, so we want to look at at electric field at the surface of the spherical conductor or spherical charge. So we want to look at the surface now. So in this case, we are considering the electric field at a point on the surface. So what it means is that we are going to enclose it with a Gaussian surface. So the Gaussian surface would lie exactly on this surface because that is where the point is. So the Gaussian surface will lie exactly on the surface of that charge. So it means the radius of the Gaussian surface is going to be the same as the radius of the spherical charge. So it means that in this case, R is equal to R. So this is true, right? Now, this is still a spherical surface. So it means if you analyze, let me not go through the whole process. If you still analyze the same way I did the first condition, condition A, you would still follow the same process and you still arrive at E, the electric field, equals the charge enclosed divided by 4 pi epsilon naught r squared. So this is what you have. You can either use capital R square or small r because both of them are equal in this case. So you should understand that the electric field at a point on the surface of the charge is still given by this, similar to the first relationship, right? Now the third one, still under this, still due to a spherical charge. The third position we want to consider is what will be the electric field at a point inside this spherical charge. We have considered first at the point outside, second at the point on the surface. Then the third one is at a point inside. What will be the electric field? So let's quickly consider that as our third application under this. So I will rub this. So electric field at a point inside the spherical charge. So in this case, the radius of the Gaussian surface, right, is going to be less than the radius of the sphere because the Gaussian surface will be inside. Now, since we're trying to consider electric field at some point, let's say this is the point we are considering at a point inside. So it means my Gaussian surface is going to be within. So this is going to be my Gaussian surface. It's going to be within the spherical charge. Now, if you watch, you would notice that your Gaussian surface does not enclose any charge. Remember, according to Gauss law, the flux that would emanate from a closed surface is going to be proportional to the charge within that closed surface. Now, our Gaussian surface, which is supposed to enclose the charge, is now inside the charge. So it means that our Gaussian surface does not enclose any charge in this case. So we can quickly note that our charge enclosed under this condition is what? 0. There is no charge enclosed in this case. So which means if we solve phi equals EA from Gauss, which is also same as charge enclosed divided by epsilon naught. Remember, we're trying to find the electric field. So if I make E the subject, the electric field is going to be the charge enclosed divided by, I'm going to take this, so I have AE naught. So the electric field is this. Now, if you recall, my charge enclosed in this case is what? 0. So if I place 0 here, I would have 0 over whatever A this. Then the electric field automatically, 0 over anything is 0. So the electric field becomes what? 0. So this is a very important point for you to note, that the electric field at a point inside a conductor with stationary charge is 0. So take note, it is applicable to stationary charge, and that's why we're still looking at this under electrostatics. So the electric field at a point inside a conductor with stationary charge is what? 0, because the Gaussian surface does not enclose any charge. So this is true. Now we are done with this first application. So the next thing we want to consider is a second application. Number 2. So we want to look at how we can use Gauss law to find electric field. Electric field due to a linear charge distribution. A linear charge. That is to say, when you hear linear means line. So say you have a wire, you have a normal wire. So we want to find the electric field. When we say linear, say we have something like this. This is a linear system. So we want to find the electric field. If this is a wire, we want to find the electric field at some point at a distance from this wire. Now, if this is a wire, this wire would carry charge all around it, infinitely long. If the wire is very long, it will carry charges around it. Now, if I consider a point like this, what will be the electric field at this point as a result of this linear distribution? That is what we want to look at. Now, say we have a wire like this. It's very long, an infinitely long wire. So say this is my wire, very long, but I just have to draw like this. Now, and it carries positive charge like this. So many. Now, I want to find the electric field at some point, at this point. Let me call it point P. I want to know what the strength of the field would be. I can check at this point, at any point. So I want to check what the electric field at this point would be. Now, if we want to use Gauss law to do this, according to Gauss, you need to enclose the charge. So I'm going to enclose this charge. And a perfect way to enclose this charge is to use a cylindrical surface this time, not a spherical surface. So I would enclose it because if I quickly draw a line through here, remember a cylinder has a high level of symmetry. So I can quickly draw the same line here so that the distance from here is the same distance from here. Then I would enclose this charge. I would enclose it. So I would enclose this in a cylindrical surface. So I'm trying to find electric field. Remember, since these are positive charge, the electric field would be pushing out like this. The electric field will be moving out like this, right? And this is the surface. This is the surface I'm considering. This is the surface. So you would notice that the direction of this surface is also like this. So this is the direction of the surface, right? So we want to check electric field at this point. We want to check electric field at this point. So what are we going to do here? You also recall that phi from Gauss law is what? You are correct. Charge enclosed divided by epsilon naught, right? Yes, and then Gauss law again is phi equals EA. Now, we want to introduce two concepts. Since we are considering a linear charge distribution, we're going to introduce a linear charge density because the charge will be distributed along a length, and the length, say the length is L. So the charge will be distributed along the length, right? So we want to consider a linear charge density so that we can eliminate Q. Since we're not talking of just one charge, we have so many. So let's use a better term to describe that. It's going to be the linear charge density. So linear charge density, lambda, I'll still write the meaning. Lambda is charge enclosed divided by the length. Charge per unit length is what you call linear charge density. So you should know that whenever you talk about density, it's always a quantity over length or over area or over volume. So we're talking of linear charge density. So that if I make charge the subject now, I would have that the charge enclosed is going to quickly be lambda L, right? Now what I'm going to do, I'm going to combine these two formulas like we have always done. What are we trying to find? We're trying to use this to find the electric field. So if I equate these two, I would have that EA is equal to what now? The charge enclosed, right? Now what is my charge? Okay, let me quickly write it. Charge enclosed divided by epsilon naught, right? Now, what is my charge enclosed? Please bear with me. My board is really small. So try to always take note so that when I rub, you still follow what we're doing. So I'll drop this part so that I can use the space there. So now what is my charge enclosed? My charge enclosed is lambda L. So I would quickly say EA equals lambda L divided by what now? Epsilon naught. Now, if you check, since this is a cylinder and this is the point, the surface we are considering, not this part. We are not considering this surface because the electric field through this point is going to be zero because it will be parallel to the surface. So the electric field at this point, this surface is the curved surface area of a cylinder. So if you are considering this, say this is a cylinder, for example, this area is a curved surface area. You can see it's a curve, right? So that's the curved surface area of a cylinder. And what is the curved surface area of a cylinder? You are very correct. The curved surface area of a cylinder is 2 pi RL. So we have that E times the area, which is 2 pi RL, right? Is equal to, what is the radius? The radius is simply this distance. This is the radius R, right? 2 pi RL equals what now? Lambda L divided by epsilon naught, right? So what you observe from this relationship, you would notice that L would fizzle L. So that if I make E the subject, I would have that the electric field is going to be lambda divided by what now? 2 pi R, then what? Epsilon naught. So this is the formula for electric field due to what? A linear charge distribution. Due to what? A linear charge distribution, or you can say line charge distribution. So this is the electric field, where lambda is linear charge density. Lambda is linear charge density, and it has a unit of Coulomb per meter. Coulomb per what? Meter, right? Yes, so this is it. Then the last application I want to look at is application 3. So I'm going to rub this. Now, if you have watched this video up to this point, I would encourage you, if you value what we are doing, I would encourage you to subscribe to my channel. Like, whenever you watch the videos, make sure you like the videos, comment so that this can reach a wider audience, and then share with your friends so that they can also benefit. Thank you. Now let's do the third application here. The third application is electric field. So how can we use Gauss law to find electric field? Electric field due to an infinite plane sheet of charge. So we have a plane sheet. What do we mean by plane sheet? Let me get one. So this is a plane sheet. One of the plane sheet does not necessarily mean blank sheet, but then a surface like this, right? Yeah, so if you have a surface like this, so it means you would notice that there will be so many charges on it, right? So if you have a surface like this, what will be the electric field at some point from this surface? That is what we want to consider. That is what we mean by an infinite plane sheet. When we say infinite, it means that the plane sheet is very big, so that you have so many charges that you can't count on it. That's what we mean. Plane sheet means a plane surface, right? This board is also a plane sheet. So that is what we're talking about. Now, say this is our plane sheet. Say this is our plane sheet. That has charges, so many charges, which I won't draw all of them. Positive charges, of course, is what we are considering. So we have this. Now, if we want to find the electric field at some point, maybe above or below, because the electric field would emanate. Now, what I'm going to do is, I'm going to enclose this, because according to Gauss law, you would always need to enclose that charge with a surface. So I'm going to still enclose. It's a perfect system to enclose this with. It's still going to be a cylindrical surface. So I'm going to enclose this with a cylindrical surface. So I'm going to draw like this. Don't mind my drawing. I'm just trying to paint the picture so that you can understand, right? So this is what we mean. So this is our cylindrical surface enclosing this plane sheet of charge. So you have so many charges, right? So these are cylindrical surface. Now you would notice that the electric field due to this plane sheet is going to point upwards. So it's going to pass through this surface and then pass through this surface, because the electric field at this surface, this ends, is going to be zero. So the electric field is going to be through this, because at this point it's perpendicular. At this point also is also perpendicular. So you're going to have electric field at the cross section of this cylinder up, and also at the cross section of this cylinder down. So that is where you're going to have electric field. Now, what it means is that the total electric field coming out from this plane sheet through the top surface and the bottom surface is going to be this plus this, right? So the total electric flux, sorry. So the flux, total flux, is going to be EA from up plus EA from where? From the bottom, right? So that my total flux is going to be what now? 2EA. So this is what I would have as my total flux through this surface. Now, remember, we're trying to find electric field at some point, right? Now, also, according to Gauss, phi is equal to what? Charge enclosed divided by epsilon naught. So if I equate these two, what would I have? You are correct. I would have that 2EA would be the charge enclosed divided by what? Epsilon naught, right? So that I'm going to make E the subject. So if I do that, I would have that E is going to be charge enclosed divided by what now? 2A epsilon naught, right? Now, but we are not done. If you notice, we are looking at, okay, we are looking at a cross section, right? So we're going to still change this charge enclosed because we have an infinite plane sheet. So the same way we did for linear charge distribution, we have to change it to linear charge density. So we're going to do the same thing for this sheet. So we're going to get this sheet has an area, but in the other case, that one has a line, a length. So but this one now, this sheet has an area. So we're going to use surface or area charge density. So but we use the word surface charge density. So I'm going to rub this. So we're going to introduce surface charge density, and surface charge density is denoted as this. So surface charge density is going to be the charge divided by what? Area. Since we are considering surface charge density, or you can call it area charge density. Now, if I make the charge enclosed, the subject, I'm going to have sigma times A, so that I'll quickly replace this charge enclosed with this times this to finally get my formula. So E is going to be the charge enclosed, which is this, divided by what now? 2A epsilon naught. So what do you think would happen here? You are correct. A would fizzle A, right? And then we can have that E is equal to now the surface charge density divided by what? 2 epsilon naught. So this is our third and our final relationship or application using Gauss law. Now, one of the things you should note, so first of all, let me mention to you that sigma, this is called surface charge density. So you take note of this. And then secondly is that the unit is coulomb per meter square. Coulomb per what? Meter square. Don't forget. So you can always identify these things in a problem from their units. Coulomb per meter square. So this is it. Now, one of the things you should take home from this formula is that the electric field, you'll notice there is no distance here, right? There's no area. So the electric field, due to an infinite plane sheet, is independent of the distance. Is independent of the what? Distance, since there is no distance here, there's no radius. So it means that the electric field, E, at some point, is independent of the what? Distance from that point. So please take note of that. And then for the previous one, electric field due to a linear charge distribution, you'd notice that the electric field is dependent on distance, right? So let me quickly summarize the formulas, the two major formulas. So the first is electric field due to a spherical charge. Due to a spherical charge, we got condition A, and we said condition A, the electric field is what? Is the charge enclosed divided by 4 pi epsilon naught times what? R squared. This is the first condition. Then the condition C, due to a spherical charge, we mentioned that E is charge enclosed divided by 4 pi epsilon naught R squared. We can still say R, right? Then condition C, we mentioned that E, electric field, still due to a spherical charge. This is at a point outside, this is at a point on the surface, an electric field at a point inside the spherical charge, you said it is what? 0. So this is very important. So this is due to spherical charge. So this is due to spherical charge, these three conditions. So this one is too important for you to note. Electric field at a point inside a spherical conductor is 0. Why? Because this conductor or the Gaussian surface does not enclose any charge. Then number 2 relationship we got is due to linear charge distribution. Linear charge linear charge, and we said it is E, which is equal to lambda divided by 2 pi r epsilon naught, right? And then number 3 is what we have here. So take note of these relationships. So number 3 is due to what now? An infinite plane sheet. Infinite plane sheet of charge. So these are the 3 things, 1, 2, and 3. You take note of them. This depends on distance. This depends on distance. This depends on distance. This is 0 at a point inside because there is no charge enclosed. This depends on distance. Inverse, right? Is an inverse relationship. But this does not depend on it, on distance. I believe that these concepts are very clear to you. Do well to subscribe to my channel, like my videos, comment, and share with your friends so that they can also benefit from this, right? I believe this is very clear. In my next video, I'll be solving problems under this application. Do well to like. Thanks for watching. Remember, this is Prime Concepts. Thank you.